To the third part of the lecture, which is the main part of the lecture, which is the soil classification. To classify soil, I have to know the geological background of the soil, the origin, and the grain size. If I want to classify a soil, it's either I classify based on its geological classification, what geologists classify them, or the origin. Was it a rock and then disintegrated, or was it transported from one place to the other? Or I can classify it based on the soil particle. I may tell you that this is sand or this is clay, mainly depending on the size of the particle of it. So there are many ways for classification. If I want to classify students, I may classify them boys and girls. I may classify them first grade, second grade, third grade. I may classify them living in Cairo or living outside Cairo. I may do lots of classification. The same I do with soil. So geological classification, we have something called residual soil or transported soil. By the way, this term is very important for us as engineers. If I tell you that I have residual soil, or if I have transported soil, it rings many bells in your head. If I tell you that this is a residual soil, it means that it has been there in this place long time ago. So most probably it is very strong, because it was born there and it remained there, so it is compacted. But if I tell you that this is transported, it means that maybe air transported from one place to the other, so it is distorted. It is not in the original shape that it was created at its original place. So residual and transported. In definition, a residual soil is a soil material which is a result of weathering and decomposition of rock that has not been transported from its original place. It was rock, disintegrated to be soil in place. It did not move. The other is the opposite. It disintegrated, but it moved later from one place to the other. So this is by definition. As in density, we said that density of the transported is expected to be less than the density of the residual. Mechanical properties. The mechanical properties of the residual, of course, is better than the mechanical properties of the transported. So this is the first definition. The second classification is the origin. Is it organic or inorganic? What is organic soil? Organic اللي هي التربة العضوية. Organic soil. Organic is very bad, because if I tell you that this is organic, it means it can disintegrate. It means it can change, react chemically, change in shape, change in size, change in everything. So it is not the type of soil that you can put your building on top of it. عاملة زي سبخة. السبخة الكولية نسمع عن السبخة. أرض this is سبخة is not good soil. Peat is another type. It's not a very good soil, and it disintegrates with time because it reacts internally. So I cannot put my building on top of it. So if I have something called organic soil, I have to remove it without doing any tests. Organic soil has a smell. You can smell it on site. So once you know that this is organic, take it outside. Don't do anything with it. So it has offensive odor. You can decide that it is organic. Of course, inorganic, this is the one that we need. If we decide to analyze or classify the soil based on the grain, then this is I have to put sizes for each grains. You know sieve, المناخل. I take a big sample, I put it in a sieve with very big openings. So most of the sample will pass. You've seen the sieve analysis. So this grain size is based on the sieve analysis test, and this is a description of the sieve analysis test. The difference between sand, this is here cohesionless soil, and this is cohesive soil, which is clay and silt, and this is sand, gravel, and boulder. The separating sieve is sieve 0.06, which we call sieve number 200. This is a very famous sieve. These are the tabulated form for this analysis. Another, you know that there is a limit for the sieves. It starts to decrease till you reach, you cannot use less than that. Then you have to change the way. I can use sieve analysis for big particles, smaller, till I reach a level I cannot do, which is sieve number 200. Yes, 200 is between the fine and the, yes, sieve number 200 is the sieve separating between the fine, which is here, yes, between the silt and clay and the sand and gravel. So once I reach sieve number 200, I can transfer to another way of testing the material. The other way for testing the material is something called mechanical sedimentation or hydrometer test. This is the mechanical sedimentation or the hydrometer test. Consider it a device. Before going into this, I will just tell you. Have you been before swimming in a very salty water, in the Dead Sea? You find that it's very easy for you to swim in the Dead Sea. Why? Because the amount of salt in the water is high. So this test is based on this. When you have particles that is suspended in the water, then the upthrust force is high. When it decreases, it means that the amount of dissolved water, the dissolved particles inside this water decreased, and so on. So they graduated this small equipment. They put numbers here, and you take the particles, put it dissolved in water, put it in this big jar, and you just put this device inside. Take the reading and write it down. Then after 5 minutes, say, take another reading. Another 10 minutes, take another reading. And so on. Every period of time, you take another reading. Every time, what happens? Part of the sediments settles down. So the amount of particles swimming in this water decreases. So the more something is sedimented, the more the different the reading you are going to get on this experiment. So finally you get another way for categorizing your soil without using the sieve. So it's either the sieve analysis, this is a description of the sieve analysis, and how we put what inside. This is the steps of the experiment. Of course, you know it and you don't need to memorize it, you just understand it. And this is the table we do for the sieve analysis. And this is the graph we do for the sieve analysis, but it ends up with sieve number 200, which is separates between the sand and the clay, or silt and clay. Once we reach this, of course, here you have two things. There is something called D10, which is the diameter of the sieve that passes 10% of the sample. And there is D60, which is the diameter of the sieve that passes 60% of the total of the sample. These two numbers are important. You just take it, divide them by each other, you get something called CU, put it in this equation to get CC. This CU and CC are very important in defining the sample and how is it very well graded or it's not graded. What do I mean by very well graded? What is graded sample? A graded sample is the sample that includes all the sizes, enough quantities of all the sizes. If I go into a class and I find that we have tall students, short students, minimum size, and so on, I say that all the spectrum is there. I can all the heights are there. But if I go and find that there are very tall students and dwarf or very short students, I find that there is something wrong. There is a gap. So this is the same in soil. If all the samples are, if I have a very well graded sample, it means that all the sizes are there. Why it is important? Because if I have all the samples, it means if I try to compact this sample, it will be easy because I have all the sizes. If I have a space that needs a small particle, a small particle will come and fit inside. If I need in between another very tiny particle, I will take a very tiny particle and put it. So I will end up with having fully compacted sample. But if I have all the samples the same, like if you know the البلي اللي كنا بنلعب بيه, the beads. If you have a jar full of beads, you cannot compact it because you will still have always voids. So, but if you have beads, very small beads, big beads, so every time you will have you will be able to compact. I remembered something, I have to say it. It does not belong to this lecture, but I have to say it. It is very important. You remember a video that was on the net speaking about a professor who brought a box full of balls, maybe 10 centimeters. He asked the students, "Is it full?" They said, "Yes, it is full." Then he brought some sand and put it inside. It was full, but you said it was full, but I can still put sand. Is it now full? They said, "Yes, it is full." He started pouring water. It increased. He made this with different sizes. But what I want to say is that when you have all the sizes, you can always fit into the voids of your sample. So this is very important. The other and the last thing is the hydrometer. This is I told you that there is the sieve, and the hydrometer. What is the hydrometer? I dissolve the sample in water, I put it inside this jar, and I take this, which is the hydrometer. It's called the hydrometer. This hydrometer, I take it, it is graduated, I put it inside the water, and I take the reading every period of time. This can be transferred into the continuation of the test. You see here, this test ended here, but if I do the hydrometer test, I can continue this graph a little bit extended further. So usually in any test, you find that this test is a solid line, then it is completed with a dotted line. It means that this part was brought from another experiment, which is the hydrometer test. This ends up our lecture for today. Our lecture was the classification, the soil classification, and we studied all the possible way for classifying the soil. I hope now you can understand that before this lecture we were speaking about soil description, just description, sand, clay, that's all, yellow, brown, strong, that's all, but I can, but now if you read this lecture, you will find that we transferred our description into fixed numbers. We can compare, we cannot dispute, because if you tell me that this is very strong sand and I tell you no, it is not good sand, then what is the judge? The judge is making some experiments, checking the values with published values for the strength, and based on these values it will answer our dispute, and we will not, as an engineer, we will never conflict with each other so long that we are abiding to these rules. Thank you, and see you next lecture.